Welcome back to Cosmic Earth. Today we are looking at something that sounds totally impossible. We always hear that nothing can ever escape a black hole, but it turns out that might not be true. Back in 1974, Stephen Hawking proposed a wild new theory. He suggested that black holes actually glow. This glow is a very faint stream of radiation. Over time, this radiation causes them to shrink. Before this, everyone thought black holes were completely one-way streets. Once you crossed the event horizon, you were gone forever. Not even light was fast enough to climb back out. It was the ultimate cosmic trap. But Hawking decided to mix two different areas of physics. He took general relativity, which describes big things like gravity. Then he added quantum mechanics, which describes tiny subatomic particles. The result was completely unexpected. To understand this, we have to look at empty space. In quantum physics, empty space is never truly empty. It is actually bubbling with energy. This energy constantly creates pairs of particles. These are called virtual particles. They always appear in pairs of opposites. One has positive energy and the other has negative energy. They pop into existence, touch, and instantly destroy each other. This happens everywhere in the universe, billions of times a second. Usually, it is completely unnoticeable, but Hawking wondered what happens near a black hole, specifically right at the edge of the event horizon. Imagine a pair of virtual particles popping up right on the boundary line. Before they can crash back together, gravity takes over. One particle falls past the point of no return. The other particle is left stranded outside. The stranded particle has no partner to destroy it anymore, so it escapes into the cold void of space. To an outside observer, this looks like the black hole is emitting radiation. This is what we call Hawking radiation. But here is the catch. In physics, you cannot get something for nothing. Energy must always be conserved. If a real particle escapes, the black hole must pay the price. The particle that fell inside actually had negative energy. When the black hole absorbs this negative energy, it loses mass. This means the black hole slowly gets lighter. It is literally evaporating into space. Think of it like a dark, heady sponge. If you leave it out in the sun, water slowly turns to vapor. Eventually, the sponge dries out completely. For black holes, this evaporation process is incredibly slow. The speed of this process depends on size. Larger black holes have a very low temperature. They emit radiation at an extremely slow rate, but smaller black holes are much hotter. This sounds a bit backwards, doesn't it? You might expect bigger things to have more energy, but the curvature of space is sharper around small black holes. This sharp curve separates the virtual particles much faster. Let us look at some actual numbers. A black hole with the mass of our sun is huge. It would take 10 to the power of 67 years to evaporate. That is a number with 67 zeros. To put that in perspective, our universe is young. It is only about 13.8 billion years old. That is just a tiny blink of an eye. The sun-sized black hole has barely even started to sweat. Supermassive black holes are even more extreme. These monsters live at the centers of galaxies. They can take 10 to the power of 100 years to decay. After everything else dies, only these black holes will remain. But as a black hole loses mass, things speed up. Remember, smaller black holes are hotter and leak faster. So, as it shrinks, the evaporation rate increases. The final moments are incredibly intense. In its last second of life, the black hole is tiny, but it releases a massive amount of energy. It goes out in a spectacular flash of gamma rays. It is basically a giant cosmic explosion. This final blast is equal to millions of nuclear bombs. All of that energy is released at once. This means black holes do not just fade away. They end with a sudden, violent bang. This discovery led to a massive problem in physics. It is called the black hole information paradox. Imagine you throw a journal into a black hole. The journal contains unique information. According to quantum mechanics, information can never be destroyed. You could theoretically reconstruct the journal from its pieces. But if the black hole evaporates, where does that information go? It seems to disappear completely. If the information is truly gone, quantum physics is wrong. But if the information is saved, general relativity is wrong. This creates a giant clash between our two best theories. Physicists have struggled with this for decades. One popular idea is the holographic principle. It suggests that information is not lost inside. Instead, it gets printed on the event horizon. It acts like a two-dimensional hologram on the outer shell. As the radiation escapes, it carries this printed information away. This would mean quantum mechanics is saved, but we still do not have direct proof of this. The debate is still very much alive today. Detecting real Hawking radiation is extremely difficult. The radiation from astronomical black holes is incredibly faint. It is completely drowned out by the cosmic microwave background. This background is the leftover heat from the Big Bang. Because of this, scientists had to get creative. They started building analog black holes in labs. In 2016, a physicist named Jeff Steinhauer made a breakthrough. He created a sonic black hole using sound waves. He cooled helium atoms to near absolute zero. This created a state of matter called a Bose-Einstein condensate. In this state, sound waves cannot escape certain regions. This mimics the event horizon of a black hole. Steinhauer observed sound particles escaping from this acoustic horizon. This was a very exciting moment for physics. It showed that Hawking's math is likely correct. The universe really does leak energy. Thanks for watching Cosmic Earth. If you enjoyed this journey, please hit that subscribe button. Share this video with your friends who love science. Let us know what we should explore next in the comments below.